Okay, so last time we discussed some basic structures on Calabi-Yau geometry. So before returning to turn to study the general structures from this bimodal string fields, we need to understand a little bit about this period map, and in particular, this period map will play a very important role to explain the classical theory. And there's actually an interesting phenomenon here. Like, it is because of the period map that allows us to write down actually action functional. That's a very important point. But before we come to this point, let me just review a little bit about this classical aspect of this period map. So suppose this is let's say compact Calabi-Yau. Compact Kähler. And remember from last time, we described this local moduli of complex structures. And you can describe this one algebraically or in terms of differential equations, and geometrically such a point is described by a polyvector field of type 1,1. Satisfying the Maury-Cardan equation. And to get the moduli, I have to model these gauge transformations, like gauge equivalence. And I explained that this moduli is smooth, locally of the dimension like H1 tangent bundle. And so we're going to write this notation like x mu to be the moduli, the complex structure on X with this particular choice of moduli. Okay, that's the basic setup. Now, we first need a little bit about some geometry of this moduli space, how to describe this one, and how to write down some coordinates and equations. So, assume, suppose this is VI, local holomorphic coordinate. And one way to describe this complex structure is the following. Like, then we can write this mu as like explicitly in such a form, mu ij bar. And then when you have the solution of mu like that, you can write down the complex structure, like the new holomorphic one form in this complex structure by dvi plus mu contract with dvi. So this is a local one form. Especially this contraction means like contract this vector field, and when you get something like dvi plus mu ij bar dvj bar. And you can write this one as the following expression, and this expression will be important. E to the mu contract with ddi. This is like you basically do this one as a Taylor series expansion, and so this is first term and second term. The higher term vanish because it's one form. But later on, you will have contributions from higher forms. And this one form local local basis of this 1-0 form in the new complex structure S mu. Okay, that's the basics data arising from this local deformation theory.
So this is the same for generalized Calabi-Yau manifold?
Generalized complex, I think so. It's like even for generalized, not only for Calabi-Yau, generalized scalar, I think it's true. Not for only for Calabi-Yau, yeah. And actually, this is an interesting question. Like the kind of like the Bezier interaction that I'm gonna write down for the classical action functional. So should suppose, I think it also exists for generalized Calabi-Yau, but I don't think anybody has tried to write anything about it. But I think it's true. Okay. Now we're gonna study the Hodge bundle. Like let this bundle HD. By the way, my Calabi-Yau is has complex dimensional D. And let this one on the moduli space, the local moduli. It also exists globally. Denote the complex vector bundle each fiber describes the cohomology class, like the RAM cohomology class at this particular point. So with fiber, say at each point here, the corresponding element is the RAM cohomology of this one. And you see, like this, because it's the RAM cohomology, it basically is rigid. It doesn't change. So it doesn't change when you change the moduli. So you can basically write down a flat connection for the bundle. That's called Gauss-Manninen connection. So we have a Gauss-Manninen connection, flat. Let's write this one as like Gauss-Manninen. And under this flat connection, you basically identify all the fibers nearby. Identify all the fibers nearby to the central fiber. So we're gonna do this anyway. At least locally. And globally, there's an issue about this monodromy, but locally, there's a canonical way to identify fibers using this flat connection.
So this is the algebraic RAM cohomology.
This the smooth the RAM cohomology. Yes. And this is really the RAM cohomology. It's a complex valued. So. Literally, this is the RAM cohomology. That's the RAM cohomology. And also, there are a bunch of interesting like subbundles, holomorphic subbundles of this guy, and as follows. Coming from the Hodge filtration, let's say FP. And on each fiber, this FP, this Hodge filtration, just pick up, for example, like say at the fiber at the point x mu on this new complex structure is given by some, like say, And as a vector space, this is what this, the fiber of this bundle is. And you can show this is actually a holomorphic subbundle. And that's very important. And there's also some kind of Griffiths transversality, which says like if you apply Gauss-Meinring connection to this one, you can decrease this filtration at most by 1. We're going to use this later. And in particular, this one interesting bundle that we use a lot is because we are working with like Calabi-Yau, there's a particular Lie bundle which pick up the Calabi-Yau volume form. Like we're gonna write this as a Lie bundle, and you just pick up the holomorphic volume form. And this is a holomorphic Lie bundle, which is called vacuum Lie bundle in physics terminology. And as we will see, actually, invariance in the B model actually lies in different sections of tensors of this Lie bundle. Okay. That's the first thing I want to explain. Now, with this data, we can write down the period map. Now, so this period map locally is given by, say, this moduli space mapped to the projectification of the Durham cohomology, where you basically map a point here, which is the complex structure specified by mu, to, and you can show actually if you deform it, it's still a Calabi-Yau, and there's a unique Calabi-Yau volume form up to rescaling, and this is the send this one to the Calabi-Yau volume form, and it's uniquely determined up to a rescaling, so it mapped to here. And this is like a local period map for Calabi-Yau manifold. So omega xu a priori is element in the cohomology here, but under the Gauss-Meinring connection, this guy can be identified with the central fiber locally. And this one is the non-zero Calabi-Yau volume form. Okay, there's a bunch of important properties about this map. First one, this map is actually an embedding. Let's call this map, let me write it. This period map. It's local embedding. So this is local Torelli. So we're gonna write this as like this. It's really embedding. So you embed this moduli space, which is highly nonlinear, into this sort of linear space. And for convenience, it is actually also useful to just remember what kind of volume form it is. Because here is only determined up to a rescaling, but it's going to be very useful to remember the particular volume form. So you can do the following. And we can write this moduli space as you see like the total space of the Lie bundle with 0 deleted modulo the 6th direction. let me write this one as an extended moduli space. Let me put a hat here. So this is like C-star bundle. Over this moduli space. And you can see from this data that this moduli space, a point here represents on the base a complex structure, on the fiber a choice. This is a vacuum line bound, a choice of the volume form. Okay, so in a sense, this one is basically the modular space of the pair. Local modular space of deformation of the pair. And similarly, we can embed this moduli space into the linear vector space. By the same reason. By sending a pair here, like say x mu, omega x mu. Now you have to remember this information about which volume form it is. You can just map it to this particular volume form. Okay, that is the period map. Now I want to explain to you the geometry of this period map, and which will motivate us to understand a particular action functional for the beam model.
How much of this work for Calabi-Yau category?
For Calabi-Yau category, I think the period map works for Calabi-Yau category. This is like a periodic cyclic homology.
And you get
Yeah.
local Torelli.
Local Torelli, I don't know. I believe it's true, but I'm not sure whether this is proved or not in some statement. But it's a calculation about this Hochschild homology.
So you also pick the choice of the homomorphic volume. So the dimension is
I don't know, the Calabi-Yau volume form, I'm not sure about that. But you see on this periodic cyclic homology, the Gauss-Meiring connection exists. We know that it is given by this Getzler's connection. And the Calabi-Yau volume form, whether it's unique or not, I'm not quite sure. If in the case it's unique up to natural homotopy, then we definitely have this kind of data. It's a good question. I don't know.
Is this global Torelli model for Calabi-Yau?
I don't think so.
Is there a contact example?
I don't know. Yeah, I don't want to talk about it. You know this. It's recorded. Okay. Yeah. Now, before we come to the classical action, let me say a few words about this period map. So let me first work on this Calabi-Yau threefold and to explain some very classical, traditional discussion on the beam model. And then we move on to modern perspective. So let's consider Calabi-Yau threefold. And on this threefold, you can use integration to define the intersection pairing. Which is a symplectic pairing. I can write it as omega. So if you look at the pairing omega alpha beta equals integration alpha wedge beta. Okay. Now, this pairing is pretty topological, and with this pairing, if you look at this Hodge filtration, one of the important properties is to observe like F2 this filtration, which is the sum of like H30, there's some H21. It's actually a Lagrangian subspace of this H3. Okay, this is a very important observation. Now, we can work this one in family, like on the moduli space. Let's say, in this case, we have the bundle like H3 over this moduli space. And this intersection pairing basically defines the pairing on the bundle. So omega defines like a fiberwise simplicity pairing. And you see, like, because this is defined in terms of smooth data, it's independent of the complex structure. So this pairing actually is flat under the Gaussian-Menning connection. So let me write it in such a way. This pairing is actually flat. Okay. Now, and then you look at this construction. If you look at this construction, like at each fiber, and you will find a holomorphic subbundle, which is actually a bundle of Lagrangian subspace. So it gives like holomorphic family of Lagrangian subspaces. Okay, now here's the key observation. You see, we have the pairing map. And you can embed your moduli space using this pairing map. Let's say look at the extended one. Embed this one to H3. And then we identify each fiber using Gaussian connection by the central fiber. So we have a natural embedding. And this guy is actually a linear simplicity space. The observation is like this embedding defines a Lagrangian submanifold. And this is a very important observation. So let's quickly prove it. Suppose you write down a family of like the corresponding family of volume form. So holomorphic family, Calabi volume forms. Parameterized by this parameter S. And now you want to calculate, for example, the tangent bundle of this one. You want to say every tangent plane is a Lagrangian linear subspace of this guy. So if you calculate the tangent plane, you basically calculate the Gaussian-Menning connection, and by the Griffiths transversality, if you take this variation, this one actually lies in F2. This is by Griffiths transversality. And you see, like this is a really every fiber. This is like a linear Lagrange subspace. So this proves the statement. So this is like a linear. This is really a Lagrange submanifold. And later we will see how to generalize this one to incorporate with gravitational descendants and to write down the full version of this model. But this is like fundamental example. Now,
How can we do this? What is the analog for other dimension?
I will come to this one in the second lecture. Yeah. But let me say just say a few more words about the classical way, like how physicists describe the B model. I mean, from this data. Yeah, I'm not sure whether like students nowadays learn this stuff or not, but this is very important from the conceptual point of view. So let me just quickly say this. Now, from this data, you can cook up the invariance, the B model invariance as follows. So choose a splitting of this guy. It's a Lagrangian splitting. So let's call this one L. Be a transversal linear Lagrangian subspace. So with this choice, we can write this H3 as, let's say, this Hodge filtration F2, direct sum of this splitting L. It's isotropic splitting, so both are Lagrangian subspace. And once you have this choice, you can write this simplex space as the cotangent bundle. So this one allows to like this space as the cotangent bundle. So this identification depends on choice of the splitting cotangent bundle of the F2. So I'm gonna write this one, just call this one F2 for simplicity. And now let's draw a picture. So you have this linear space. This is the original linear space for the period. And now, by choice of the splitting, you identify this one as a cotangent bundle. So this is the base. And now you have the period map, which is the Lagrangian subspace, which embeds your modular space of the pair. And with this choice, you know, like whenever you have this kind of picture, it's a Lagrangian submanifold. You can write down a generating function. So by the proposition, so this one is Lagrangian submanifold. So it implies that we can write this modular space as the graph of a generating function. So this.
At that point, it's not transversal.
This L, I need to choose a transversal one.
In the picture, and you maybe work near the origin.
Only near the origin, yes. I really work here. I draw this like that, but it's really locally. Yeah, it's really locally. So.
So you really pick a particular complex structure because only then you have to know what happens.
Yes, that's true. Yeah. So it's actually I will do splitting for the complex conjugate splitting. Yes, you're right. But this is only local story. You're completely right. So now, but anyway, this locally you can write down a function for the generating function for this modular space. It's a function on H3, H2, 1. Now you can actually do better. So the way it goes as follows. Like, now for simplicity, let's write, for example, let's just choose my L to be H1, 2, there's sum 0, 3. This is like complex conjugate splitting. This is more standard thing you write, like, so you can decompose your H3 like the standard decomposition.
What is your F load? The F load is F of it?
F2?
No, the thing about F series in whole of F loaded.
Oh, sorry. Yeah.
Confused because the L is numeric, the whole free form, right?
No,
L is numeric.
L is a choice, fixed, choose.
Yeah, but in the local picture, then you're varying the free form.
But you see, like now, this everything's on the central fiber. This is like it's really on the central fiber.
Yeah.
It's really on the central fiber. So you see, like so this picture is really on this particular central fiber. So that's why I need to use Gaussian connection to identify everything, pull back everything back to the central fiber. So it's like the modular space is really, you see, like this map. It's nonlinear map.
That you want L at that point to be tangent space of M complex, right?
Yeah, I wanted this one to split the complex structure at the central fiber.
At the central fiber,
Yeah.
it's just tangent space, right?
Yes.
Well, the tangent space is F0, 3, 0 plus 2, 1, right?
No, this L is not the tangent space. This one is the tangent space. So
That is the tangent space. Yeah.
yeah, this is a cotangent. This is yeah, transversal one. Yeah. So this one contains like the tangent space here at 0. That literally is H3, 0.
Sure.
Yeah, it's literally this one. So this complex structure and this for the volume form. Yeah. But you're right. But the tangent, when you move around this point on the modular space, you calculate the tangent space. They change. Yeah. But locally, they still split by L. Yeah. Okay, so now with this data, physics will say, like, you can write down some kind of special geometry and write down the pre-potential, things like that. So let me quickly explain what this one means and how to generate this. Okay, so let's do this this particular splitting at the fiber, and everything you can write your function like this F0 as a function of this this parameter, which is one-dimensional in this guy. So now we just do this one explicitly, like we parameterize. This modular space because we know it's given by the graph of this this exact form, so we can just write it down explicitly. So embedded in this H3 by the following formula. So in terms of this splitting, this decomposition, so this is parameterized by like T0 and Ti, and now this is coordinate on the base. Now on the fiber is given by this exact one form, so you can write this one as like partial Ti F0 and partial T0 F hat T0. So that's how you write it down explicitly for this data. Now, you have actually a little bit more structure to say, and you see, like, because our modular space of the complex structure is really this extended modular space mod out this C star action. So basically this volume form is determined up to a rescaling. And this parameterized volume form. This means like this actually is a homogeneous coordinate on the original moduli space. So this one says the following. This one says like this guy. So the whole thing is homogeneous, means like this degree 1, this also degree 1 and degree 1. So means like this guy has homogeneous degree 2. This is the first information we have. Second, again, because of this following data, this direction parameterized the volume form. And this is really the H21 component which parameterized the complex structure. So in terms of this homogeneous coordinate, the actual coordinate on the moduli space of the complex structure is given by, like this is the standard coordinate by the ratio. So let's denote it by tau I. So this is not homogeneous coordinate. This is literally the coordinate parameterized in the moduli space of the complex structures. So local coordinate. Now you can write everything in terms of this coordinate on the moduli space, which is the base manifold. And this guy is a fiber, is a 6-star bundle on the base manifold. And as follows. So because of this property, we can write F0 as, you pick up the degree 2 component and write everything else in terms of this non-homogeneous coordinate. So we can write it as like T0 square. And in terms of function of tau. Homogeneous. The whole thing is homogeneous coordinate. So this one is homogeneous degree 1, because but it's
for the line bundle,
yeah. For the line bundle, rescaling of the line bundle. And so this one has homogeneous degree 2 under the rescaling, that's why people say like the generic zero event is information is about sections of the like a tensor of the vector line bundle twice. This rescaling will be also important when we discuss the open close. But anyway, this is I want to spend some time to discuss this. So probably just let me say in words. Just as Yalong explained, as the question is about saying that this actual element is a section, a local section of the vacuum line bundle tensor, like -2, something like that. L is a vacuum line bundle. Just a quick remark.
Sorry, L is F2.
No, L is a vacuum line bundle. Now you can say actually a little bit more than once you have this data. You plug in this expression F0 hat into this homogeneous coordinate, and what you find? You find like this modular space is parameterized by the following homogeneous coordinate, like T0, T1, and now you take the derivation for Ti, but the whole thing it can be written in such a way, so you can turn this derivation in terms of tau I and then T0, and I think this transient variable is not hard to see. Is given by the following, like probably let me just write T0 multiply everything by 1 tau I. This is the first place you're going to see this flat coordinate in this kind of a primitive period map. T0 tau I and partial tau I F0, and the last term you will discover like twice F0 minus tau I partial tau I F0. Yeah, you just plug in this guy into this expression. You will see, you will see everything is homogeneous. You pick up T0 as a common factor, and the rest going to be a function of tau. And this factor is the analog of so-called primitive period map. We're going to discuss it later as well. But anyway, so you see, like once you do this, you find a particular parameter, like family of the volume form by this particular expression. So let me just write it down. You can. This is really about the choice, a choice of the volume form over the Calabi-Yau moduli space by this guy. 1 tau I and partial tau I. Yeah, physicists would say like use special geometry to cook up this data, but essentially the same thing. Now, with this data, you can calculate with this particular choice of volume form. We'll see later. This is the analog of primitive form. With this particular choice of the volume form, you can calculate, for example, this equal coupling, like say IJK.
Are you writing the form or you writing the class?
No, it's a particular. It's really a class on the fiber, but it's a specified family. It's a specified section. It's a section of the bundle, so it's a class. Yes, right. And now with this, probably better to write in such a way. So you can calculate the equal coupling of the moduli space by the following: like you do Gauss-Bonnet connection, like tau I for this particular family. And you wedge with like second derivative with respect to the Gauss-Bonnet connection, like tau j, tau k, this volume form. Now the trick is to see like because of the form of this family, you take derivation for tau. This becomes constant, and this becomes 0, and something else. Then the reason this one is called a flat coordinate is because you take the second derivation. This will go away, and you end up with something on the right. And then the way you calculate this intersection pairing is going to be only this component intersect with this component. And this is an exercise for you. It's a very good exercise. You will find like this is equal to partial tau I, partial tau j, partial tau k, F0 tau. And this element is called prepotential in physics literature. And that's how.
What if you just differentiate 3 times and then gradually the one?
Yes, the same.
Right?
Yeah, the same. Yeah, because this pairing is compatible with the Gauss-Bonnet connection. Yes. But the reason I write in such a way is because this argument generalizes like literally to all the other cases, like extensive period map, like primitive period map, all these kind of things. The same argument.
The argument that they're the same because somehow should be able to. This is the branching of the problem.
Yes, exactly. Yeah. So we'll see actually in the next lecture. Yeah. Okay, the last comment before we take a break is the following. We need to understand a little bit about the structure in terms of concrete data. So we need to describe a little bit about this deformation theory of the pair. To the what? To the.
Yeah, the G, but the other track coordinate. The other, I mean, you can go from this specificated geometry.
Yeah.
Go from F to G to F.
Ah, yes. Yeah. But there are actually some other choices. I mean, yeah, so, yeah. But anyway, so let's discuss this pair deformation a little bit, and to see what we're gonna do to generate this argument. So we see like we want to understand how to deform the pair. So one is the complex structure, one is the holomorphic volume form. So we know like first deformation of the complex manifold is described by a Pauli vector solving the Maury-Cardan equation, modular gauge equivalence. Okay, that's something we know already. And then we know, let's specify this new complex structure as x mu, the same notation. So this is in mu complex structure. Now on this new complex manifold, and the new 104 is spent by the following, like so e to the mu contract with dzi. This object explicitly is given by dzi plus mu contract dzi, and no higher terms because of the by type reason. This forms a new basis. One-zero form. Now, okay, so here's the lemma, which is very simple to show, but I can leave this to you.
Then you're back to calabial organization.
Which one? The general, yeah, general, yes. Dimension x is d. And you calculate this operation e to the mu, like contract differential forms. And for example, if you contract two differential forms, like alpha wedge beta, this equals e to the mu contract alpha wedge e to the mu contract beta. This basically says like this one behave like a group action, like it's a transformation for any differential form. This is a straightforward calculation. So I gotta leave this to you. And this implies the following: like if you apply this lemma, you find like so originally on the manifold, if you choose some kind of local holomorphic coordinate, you see like dz1 wedge d. So locally, this is like a spans it's a holomorphic volume form on your Calabi-Yau manifold. Now you contract this one with the e to the mu, and by this lemma, this will apply to dz1, dz2, etc. So this form is actually a d, 0 form in the new complex structure. Locally.
So you do the omega x then?
Yes, you do the omega x, it will be, yeah. So this is like it's like type d, 0 in the new complex structure. So as Conan mentioned, like if you apply this argument globally, you will find like e to the mu contract this volume form, the original volume form, becomes it's not a Calabi-Yau form on the new complex structure. This is actually is of type d, 0 in the new complex structure, but it's still not yet a Calabi-Yau volume form. So to be a Calabi-Yau volume form, you want this one to be holomorphic. So not yet. But because of the type reason, we know like the new holomorphic volume form must be this guy multiplied by some kind of smooth function. So invertible smooth function. So Means like there exists a smooth function. Let's call this one rho, such that if you rescale this form by this vector, so by e to the rho, and then e to the mu, contract with this is literally just function because rho is a function. This is a polyvector field. The whole thing again is a D, 0 type, but after you rescale, you can find a holomorphic volume form. In the new complex structure. So let's write down the equation. So now, what's the property for this one to be a holomorphic volume form? Because the type is D, 0, this one is holomorphic if and only if this is closed. So this holomorphic property is the same thing by the type reason as saying that this is applied D, the Raman differential, to this guy. Actually equals 0. So this equation describes the deformation of the Calabi-Yau volume form. So we can write it down. Exercise. To show that we find the following two equations. The first equation is the equation for complex structure. This is for the form x. Then second equation coming from this one, it can be written as like d bar rho plus this is like a divergence operator applied to mu, and plus bracket mu rho equals 0. So this equation describes the deformation of the corresponding Calabi-Yau volume form. So it deforms to x mu and deforms to omega x mu. So these two equations are the equations describing the deformation of the pair. This is also extensively studied by Barnikov in his semi-infinite structure.
So besides the smoothness, everything works for non-Kähler set.
That's true. Yeah, that's true. The Kähler stuff is used in the Dirichlet-Lamé argument. And yeah. I think we take a break now. We're gonna continue to explain this equation and its generalization to extend the period after the break.